Welcome. In this video, we are going to walk through the initial 3D Gaussian Splatting paper. The content of this video is extracted from my course on 3D Gaussian Splatting, where we implement the initial paper from scratch using PyTorch only, okay? So no C++, no CUDA, just PyTorch, and we are not going to use any external 3D libraries. Everything is implemented from scratch. If you're interested, I will put the link of the course in the description, and I hope you will like the content of this video. So let's dive in. Let's dive into the great 3D Gaussian Splatting paper. Basically what they said, they introduce a 3D Gaussian scene representation together with a real-time differentiable rendering. We're going to discuss that in a bit, but that's really nice. That's great to find a great scene representation. But if with this representation, you do not have a proper way to first render it fast, but also render it fast in a way that enables optimization, and that enables training of the scene representation, then it's useless for 3D reconstruction, right? Mesh are really great. We can use them for, they've been used for decades for scene representation. But if you want to learn from images a mesh scene representation, it's very difficult. There are more and more approaches that do that, or that do that for simple scene. Maybe we'll eventually reach that, but nowadays we are far from it. So today, for 3D reconstruction, novel view synthesis, if you come up with a new scene representation, like this one, 3D Gaussian, it should be coupled with a proper rendering engine that is differentiable and that is fast, okay? Because if each gradient step takes 1 hour, it will take years for the model to converge and to learn the scene. So it's not useful. For a quick story, I met the INRIA people a few months ago at a machine learning conference. They told me that initially when they were designing this paper, everything was much too slow. And then just one person, there was someone that just arrived in the team and that had experienced with GPU programming and with custom CUDA kernels. And that's really what made the difference. At the beginning it was too slow, but with proper CUDA kernels and GPU optimization, they were able to make this really great approach that nowadays is used by everyone. Okay, so they mentioned a NeRF, neural radiance field. NeRF requires neural networks evaluation. For rendering an image, for each pixels, you need to query the neural network hundreds of times. If that's a 1 million pixel image, that means the neural network will be queried 100 million times. And therefore, even if the neural network is small, it's fast to evaluate. Generating the image is costly. Okay, we're going to discuss that later. But NeRF needs to model the full 3D space, while approaches like point clouds, mesh, or Gaussian splatting, they only need to model the non-empty space. And therefore, that's a huge cost. That's a huge gain in terms of compute. Okay, so first thing, they start from sparse point clouds, okay, produced during the camera calibration, usually with CalMap, or more generally with SFM. So basically, they leverage this point cloud that is extracted during the camera calibration, and they use that as a strong initialization for the Gaussians. At the end of this paper, they do ablations where they show using from the, starting the initialization with the extracted point cloud versus starting from scratch, and we'll see that it makes a big difference. And as we said, it avoids unnecessary computations in empty space. Second thing, we are going to discuss that in a bit, but they have some interleaved optimization on density control of the 3D Gaussians. So basically that means that when there are Gaussians that become a bit useless, they prune them, they remove them from the optimization. And when there are Gaussians that are too big, or that some regions are over-reconstructed or under-reconstructed, they have some strategies to duplicate or to clone or to split the Gaussians so that you really adapt the density of your Gaussians and it really adapts to the scene. And therefore, for a lot of scenes, you can train with the same hyperparameters. You don't need to tune your hyperparameters per scene. On third, that's what we mentioned. Together with this new scene representation, we have a fast rendering algorithm. Again, that's one of the key components. A great scene representation alone is not sufficient. You need a fast rendering algorithm that should be differentiable as well if you want to do a reconstruction from images for the full pipeline to be useful. Okay, so here what they mention is that mesh and ponds are the most common 3D scene representations. They've been used for the last decades. On GPUs, they've been designed to handle those representations. So yeah, on they are explicit, right? They're explicit. That's what is mentioned. That means that, for example, if you have a point cloud, and then one part of my point cloud represents a table. If I move all the points that represent the table to the right, then my table will be moved to the right. I can do the same with mesh. With nerf, a nerf is a neural network, so it's implicit. I cannot modify objects in the scene. Well, there are papers that do it, but with the vanilla nerf approach, you cannot easily modify or change the position of an object in the scene, while with 3D explicit representation, you can easily move objects or delete them or do things like that. Okay, so yeah, what they say is that they only require SFM points as input and also the camera parameters. On synthetic scenes, they can start with random initialization of the Gaussian and they get good results. But for real scene, there is really like a big jump in performance if you properly use the SFM points for initialization. Yeah, a fast GPU sorting algorithm, we're going to discuss that later, especially when we implement the paper. Yeah, okay, they mentioned related work, point-based rendering. We're going to discuss that later. We've discussed the Pulsar paper, that's one of them. On the issue with papers like Pulsar, for example, and there are others, where you first do the point-based rasterization, and then you have a neural shading approach to correct for the noise or to produce a better final image, is that those convolutional neural networks, they usually introduce flickering, so temporal flickering. So that means that, yeah, when you generate your video, that's a video of 10 seconds, the neural network is not forced to be consistent in between frames, so you will see little flickering from frame to frame. When you play your video, you'll really see this temporal flickering. While here, what's happening is you have a 3D representation. So by itself, the scene is 3D consistent. So if you generate one frame and then generate another frame by moving a bit the camera, you are looking at the same thing. So by design, this thing is consistent, so you have no flickering. But when you get a neural network involved, the neural network will introduce some flickering, some inconsistencies. Okay, so here what we've already discussed is that point cloud rendering or rasterization, because it's a sparse representation, it will introduce holes and can also cause this aliasing on discontinuities. Okay, so here this is a bit some background on volumetric rendering. If you know NERF, you know about that. But basically here the idea behind NERF and behind also Gaussian splatting, because Gaussian splatting is a 3D scene representation that's building upon volumetric rendering. Here it's really the idea is to model your scene as a volume. Okay, so that's not the best way to model a scene, like opaque things like a wall, like a table, but it works well, right? On why we do that, it's because it allows commutations of the gradient. It's mainly due to the differentiation part of things, right? You can easily, with that representation, backpropagate and compute gradients and optimize your parameters. But basically the idea is really, let's think about NERF for a moment. So you have a pixel, you shoot a ray in the scene, and you ask yourself, what is the contribution of this ray? What should be the color of this ray, okay? And that will be the color of your pixel. And therefore, so it's really as if you were integrating a volume, right? So at every point in space, you have a color, okay? That's the color of your volume. You have a density, alpha, okay? If alpha is big, that means it's a very opaque volume. You will very opaque gas. Okay, you won't see behind it. If alpha is small, it means you can see behind it. On the transmittance, it's the accumulated opacity over time, right? If at some point there is something that is opaque, you will not see behind it, okay? Or in a way, the transmittance, it's the opposite, right, of the opacity. So basically, you progress throughout the volume. At the beginning, you see, because you've not accumulated a lot of transmittance, so you can see what's behind the cloud. And at some point, you hit a very dense part of the volume, or maybe a better way to do that is to say, okay, you model a scene with nerve. At some point, you hit a wall, so you will not see what's behind the wall, okay? So when you hit the wall, the value of the wall, alpha I, is equal to 1, okay? It's equal to 1, so it is opaque, it has a high contribution to the pixel color, but then later, T of I will be equal to 1, it's a product of all the 1 minus alpha I, and therefore, if at some point alpha I was equal to 1, Ti will be equal to 0, so that means that everything behind the wall will be equal to 0, okay? Ti kills the contribution of everything that is behind something opaque. I'm not kind of my explanation. I hope you understand, but otherwise I would invite you to have a look at this, to reread this section 2.3. You can also have a look at the NERF paper if it's not yet done. But basically, it's all the basics of volumetric rendering, okay? So for every point, or here basically for Gaussians, so basically what will happen, you will project all your Gaussians on the screen, you will sort them by depth, and then you will have a look at Gaussians after Gaussians. So for example, this term will give you the contribution of the first Gaussian. So basically, you first multiply the opacity by the color. If that's a transparent Gaussian, then alpha will be equal to 0, so it will not contribute to the color. But let's add the opposite. If that's a very opaque Gaussian, for example, modeling a table, alpha is equal to 1. So basically, the color of the pixel will be equal to color of the table. And then T of I for the next Gaussians that are behind it. T of I, because of this term, it will be equal to 0. So basically, it will kill everything behind that Gaussian, okay? Because this Gaussian is fully opaque. And if it's in between, if this Gaussian is just half transparent, then all the Gaussians behind it will have some contribution, but it will be attenuated by this term Ti, okay? So this is all volumetric rendering. And the only difference between NERF and between Gaussian splatting is how your scene representation will give you those terms. So for NERF, for example, A of I and C of I are given by the neural network. You evaluate the neural network to know A of I and C of I. For Gaussian splatting, C of I is stored in each Gaussian, and alpha of I will be a combination of an opacity per Gaussian parameter on the Gaussian kernel of the Gaussian, but we're going to discuss that in a moment, okay? So the volumetric rendering part of things, it's the same between Gaussian splatting and NERF. The difference is all things are represented, and also all the algorithm compute those equations. Basically, we could compute them in the same way as we do for NERF, for Gaussian splatting, but Gaussian splatting introduces a much faster algorithm to compute those equations. But I could take a NERF code base and just replace the computation of alpha I and Ci, use my Gaussian splatting representation to compute them. It will just be much slower, okay? Yeah. There are some papers based, before Gaussian splatting, there were some papers that were doing like 2D Gaussians, that had 2D Gaussians with some covariance. Yeah, basically maybe we can call them like precursors to Gaussian splatting. But yeah, for now we're not going to discuss about that. Okay, here I believe they said that NERF is implicit, while points are explicit, so you can, that's what we discussed previously. You can create them, delete them, move them, okay, while with NERF you cannot do that, it's just a black box neural network. on here with Gaussians or with point clouds based volumetric representation, you have all the benefits of volumetric representation. But yeah, you do not need to model the full volume, okay? When there is empty space, you don't model this empty space, okay? There is pulsar that we've already discussed about, a kind of paper that is motivated, the Gaussian Splatting paper. We discussed the type-based approach in pulsar, and it has also inspired the type-based approach in Gaussian Splatting. Okay, and they also mentioned the CNN a bit earlier. Yeah, that introduced temporal flickering. There is no need of CNN for post-processing or for shading in 3D Gaussian splatting. Okay, so as we've said, it's all great to have a nice new 3D representation, but you should be able to render it and to differentiate it in a very fast. Okay, so that's a bit what they explain. There is this approach that we've discussed, like some kind of 2D Gaussian, right? But the idea is that, yeah, you model the 3D representation with 2D points. On each 2D point also is a normal vector. But here they say that it's very difficult. Let's say that let's think about Gaussian splatting, where you initialize the Gaussian with SFM with the output of structure from motion. Okay, so let's say call map. You get the point cloud extracted from call map. It's very difficult to initialize the direction of the normal vector of each point, or then later or even if you start with a random initialization of the normal vector, then later it's very difficult to optimize it. So they say that this approach is not it's not best, and therefore they try to avoid just to focus on the 2D points with a normal. They prefer to start with with 3D Gaussians that do not require normal. So basically all the Gaussians are modeled. Obviously they're Gaussians, so they have a position on a 3D covariance matrix, sigma. And therefore the alpha I parameter that we've discussed, alpha I, it will be given by this Gaussian kernel multiplied by an opacity term per Gaussian. So basically what does that mean? That means that this density, it's very big at the center of the Gaussian, and then when you get away from the center of the Gaussians become a bit more transparent, okay? So you have this Gaussian kernel multiplied by the opacity. The opacity, it's a constant, it's per Gaussian, it's learned, and that will give you the value alpha I, okay? That's the alpha I, so it's given by the Gaussian kernel multiplied by the per opacity term. That's exactly what is described here for the 2D approach, okay? On the color, it will be learned per Gaussian. And basically now, that means with all the components we need, we can get the alpha I parameter, the CI parameter, and we just need to compute efficiently those equation 2, for each pixel in the image. Okay, so for doing that efficiently, what we do, instead of starting from the camera, or shooting rays from the camera to the scene, that's what a nerve does. Here they do rasterization. So basically it's really like graphics, right? 30 years ago, or let's say you want to generate an image, a very nice looking image. What you do, you shoot rays from the camera to the scene, you simulate the interaction of light, you do path tracing, and you get a very nice looking image. The issue is that it's slow, okay? In a way, that's what nerve does. It shoots rays from the camera to the scene. So basically what has happened in the graphics community for the last decades, instead of doing that, they've done what is called rasterization. You take your mesh and you project them from the scene to the camera. That's called rasterization. That's what we've implemented in the first part of the course. So basically here Gaussian splatting, instead of taking the first approach, shooting rays to the scene and computing this equation for each ray, they take advantage of all GPUs have been designed for the last decade. GPUs have been designed to allow fast rasterization. So here they will project the Gaussians to the screen, do the rasterization process, and then compute this equation 2, sorry, for each pixel in pixel space. Okay, So basically here they explain how to get, we will do all that when we do the implementation, but how we get the covariance matrix then in screen space, because the 3D Gaussians are projected into a screen space, and then to get the 2D covariance matrix, that's how it's how you get it, equation 5. So very easy to get, just matrix multiplications. W, it's the view transformation, so the camera toward transformation. On G, it's the Jacobian. It's the Jacobian of the transformation, of the perspective transformation, okay? So basically it's the Jacobian of the rasterization transformation. So basically projecting everything to the screen. So basically it will be dependent on the focal length of the camera, okay? So it will be dependent on the intrinsic parameters of the camera, its focal length. On W will be dependent on the extrinsic parameters, the camera position and rotation. Okay, so they say that then obviously one of the parameters of the Gaussians are the covariance matrix that we need to learn per Gaussian. So what we might want to do is just to optimize those parameters directly. But the thing is that in physics, well, or in the world, like a covariance matrix is only valid or only has a physical meaning if it's positive semi-definite, okay? So if I just optimize an unconstrained covariance matrix, it might not be positive semi-definite. So what they do a reparametrization or a specific parametrization of the covariance matrix so that it will be positive semi-definite, okay? And I can do that by optimizing a scale parameter and a rotation parameter. So that's how my covariance matrix will be represented with those two values, the scaling parameter on the quaternion that gives me my rotation matrix. So yeah, we've discussed about quaternion previously. And then we will use the function we've built to go from the quaternion to the rotation matrix. And then yeah, we can just create equation 6 and yeah, we can just implement equation 6 and get our covariance matrix, okay? Okay, here if you just do automatic, so if you implement your forward pass, and then you let automatic differentiation compute the gradients for you, it will be very slow, consume a lot of GPU memory. So instead what they do, they implement the backward pass themselves. And that's also what we're going to do when we do the training and when we train it. Okay, so as we have discussed previously, optimization is done with adaptive density control. So we initialize the number of Gaussians to the number of points that are extracted from a call map, for example, from structure, from motion. But then we want the number of Gaussians to adapt automatically. That's what this adaptive density control does. We've discussed that at the beginning. So basically that means that we want to kill transparent Gaussians that have no contribution. And when Gaussians are too big, for example, we want to split them or to clone them, okay? We're going to discuss that in a bit. Here they see, maybe that's not the best moment to have a look at this figure, but let's, because it's here, let's have a look at it. Here what they do, and maybe it's not easy to see it here, it will be easier to have a look at I think this paper, it's the compressed paper. It's 25 megabytes, but they have another paper that is uncompressed, that is more than 100 megabytes. But here what they do, they shrink the Gaussians, okay? So here we can have a look at the shrunk Gaussians. But basically the point is that after optimization, the Gaussians will be anisotropic, okay? So that means that the Gaussian have some shape. They do not have the same extent in all direction, okay? If that was not the case, if the Gaussian were isotropic, okay, that means that there is no need to load this flexibility. You could just make the Gaussians you could just restrict them to be isotropic, okay? And very likely it will make the algorithm easier to implement or maybe faster. We will see in the Ablation. Basically, here we see that's a proven fact that after optimization, the Gaussians are anisotropic. But still, they will do an experiment later in the Ablation. We're going to have a look at that. That shows that that when you constrain the Gaussians to be isotropic, you get worse results. Okay, so basically, yeah, okay. Here they say, okay, because we're doing optimization, yeah, but basically that's a kind of motivation for the density control. We want to be able to destroy geometry if it has been, let's say it's stuck in local minimum, or let's say it has been badly initialized. We want to be able to destroy some Gaussians or to move them, and that's what the density control will do. Okay, for the loss, they just use a L1 loss plus SSIM loss. So what's we powerful here is that for nerf, you just render 1 pixel at a time. Here, because you generate the full image directly, you can leverage it to compute loss on the image. You can take image 1 versus, well, ground truth versus prediction, and you can take the loss between them. So for example, you could use a VGG loss, which you cannot do with nerf, because in terms of memory or in terms of compute, you cannot render all pixels directly of the image. You just do chunks of pixels at each iteration. But anyway, here basically they have a combination of L1 loss on a SSIM loss between the prediction and the ground truth image. Okay, so yeah, we are going to discuss the warm-up. We discuss that in a bit. But basically, every 100 iteration, they remove Gaussians that are transparent. So Gaussians have a per opacity parameter. Okay, they have an opacity parameter. And when opacity is less than the threshold, that means that the Gaussian is transparent. So basically, if the opacity is equal to 0, that means that the Gaussian is free transparent. If it's close to 0, it means it's almost transparent. Well, it's transparent, but it's not invisible. But yeah, basically they delete all Gaussians that are transparent. What they need to do is to populate empty areas, and also in the opposite, like remove over-reconstructed areas, so areas where you have too many Gaussians that are too dense. I believe that's what they say. Yeah, Gaussians cover large areas in the scene. And basically, they observe that both those scenarios, so under reconstruction and over reconstruction, in those cases, you have large view space positional gradients. Okay, maybe that will be maybe you will understand that better when we implement it. But yeah, basically, a way to say that is the gradients give you. If you have a big gradient, it means you need to do a big update. You need to move your parameters by a lot. If gradients are small, you are maybe close to the optimal value. Okay, so here this so basically that means that when you have a big gradient, it means the parameters need to be updated by a lot, and therefore it's not you are far away from your optimal value. Okay. But basically, with this criteria, so basically that's an automatic way that does not require tuning, that tells you, if you need if you're in a scenario of badly reconstructed, that is over or under reconstructed, or that you need to do something. I say that it does not require tuning. It still requires tuning, right? Because you have some threshold for this positional gradient. By default, they use this value 2e-4, and they use the same one for all scenes. It's not tuned per scene. So basically, when there is under reconstruction, what they do, they clone the Gaussians. Maybe instead of having a look at the text, we can have a look at a nice figure. Let's have a look at the figure here. Okay, so basically here, this area is under reconstructed. So basically what they do, they clone the Gaussian. You have another Gaussian with the exact same shape. On here, when it's over reconstructed, when the Gaussian is covering too much of the space, you split it. Now, I don't know why on the bottom left we don't see the initial Gaussian, but basically what you do, you split the Gaussian in two. On the two new Gaussians, you make them smaller than the initial one, okay? Because the Gaussian is too big, so you split it in two, and that are smaller, okay? Great. So one last thing to discuss about that is that you can have because of the 3D ambiguity or because of the loss of information. Basically, you try to reconstruct the 3D information, but you only have access to 2D images, so there is a loss of information. On basically, you can get stuck. On that can introduce floaters, especially close to the input cameras. So basically, to avoid that, to avoid floaters, every 3K iterations, they set alpha, so the opacity per Gaussian, close to 0. Okay, so basically at those iterations, the rendered image will look almost transparent. So they set back the opacity to almost 0 for all Gaussians, and then they let the optimization push them back to some meaningful value. But basically that means that the Gaussians that are, let's say, not needed, they will stay stuck with an alpha, with an opacity close to 0, and then later they will be pruned with this strategy where you delete Gaussians with alpha less than a threshold. Okay, and that's the way to delete floaters. Okay. Okay, so basically we've discussed that in a Pulsar paper, but basically they split the screen into tiles of 16 by 16 pixels. Yeah, so basically what's happening, okay, here all these are optimization. It will be clearer when we implement it from scratch. But basically what you do, so you will treat tiles of 16 by 16 pixels one at a time. And therefore, for each tile, you will check which Gaussians are intersecting this tile, which Gaussians are touching this tile when they are projected. Because Gaussians are continuous densities, they're Gaussians. In theory, all Gaussians intersect with the tile, but we only keep a Gaussian in the tile if there is a 99% overlap. I'm not sure where this is phrased, or maybe the wording is better than mine. But basically, yeah, you take the density of your Gaussian, and if the intersection with the tile is higher than 99%, you keep it in the tile. Okay. And basically, then what you do, you sort the Gaussians per depth, right? That's what you do when you do rasterization. You sort the points or the mesh, you sort them per depth, okay? That's what you do when you compute equation 2. You start with the point that is the closest to the camera, and then you treat other ones. But here we only do one depth sorting per tile, okay? So basically that means there are approximations. You don't do a sorting per pixel, you do a sorting per tile. So it's a small approximation. That is okay, that it doesn't have a big impact, but there is this approximation going on. Okay, in terms of other optimization, if we look at equation 2, there is this term Ti. So when Ti is equal to 0, you can keep computing your sum. Okay, if we go back to equation 2. Okay, here I have a sum of n terms. But let's say that after 3 terms, so I've computed the first 3 terms, that now Ti is equal to 0. And if Ti is equal to 0, for all j greater than I, Ti will be equal to 0, Tj will be equal to 0 as well. There is no point in keeping computing the sum, because we'll just add zeros for all the next terms. So they have a stopping criteria for that. So that when the transmittance is equal to 0 or close to 0, you stop computing the value. And here it's a per pixel thing, it's not per tile. Yeah, and they say it's the only stopping criteria. As we've discussed, it's always the same hyperparameter for each scene. There is no per scene hyperparameter tuning. For the optimization, they start with some warm-up. Okay, we've already mentioned that previously. But basically, first they do the first 250 iteration at a 4 times smaller resolution, and then the next 250 iteration at twice the resolution. Okay, Yeah, so that's allowed to have very quickly a good approximation of the scene, and then we refine it at the highest resolution to get better details. When we do the implementation, when we do the training, you will see that after 500 iteration, we already have a good starting point. Okay. For now, we've assumed that each Gaussian is a color, Ci, okay? For now, it's a bit hidden, but it will be slightly more complex, but it will become very clear when we do the implementation. Each color, Ci, will be dependent on the viewing direction. That's what we've already discussed. Based on where I'm looking at an object, based on where I'm looking it from, the color can change, okay? That's a real light effect. Yeah, and that can be modeled with spherical harmonics coefficients. I've already explained that, but if you have a look at a car, for example, if you move around the car, if you look at the exact same point, the color will change, okay? Because of the lightning on the way that light from the sun or from any light source is reflected. So basically, this can be modeled by a spherical harmonics coefficient. For now, let's not discuss about that too much. It will become clearer when we... I will make some slides about them, and we will implement them, so it will become clearer. But basically, the point is that if you optimize those spherical harmonics coefficients, all of them directly, so basically here we are going, in our code, we're going to use 48 coefficients. If you optimize all of them directly, you can have some issues, or it can be stuck in local minima because of the lack of angular information. So basically here, what that means if you train a synthetic scene, such as, for example, the well-known bulldozer in Earth, where you rotate around the object, you have enough angular coverage of the object, so that's fine, you will be able to run properly. But in real life, because of some lack of some viewing direction of the object, you might be stuck in local minimum. So what they do at the beginning of training, they do not optimize all the spherical harmonic coefficient, they just optimize a few of them. But all this will become very clear later. Okay, so I think the only for the first 1k iteration, they just optimize the first 3 coefficients. Then for the next 1000, they optimize only, I think if my maths are good, it's 7. And then after 7, it's 15. I think it's 3, 7, and then all the others. But anyway, we'll see that later. Yeah, so sorry for that. Okay, the report they're running on a A6000. On my side, I'm using an A5000, which is slightly less powerful. But yeah, anyway. Okay, as we've discussed, it's very important to start with a proper initialization for Gaussian splatting. We're going to look at the ablation in a moment, so you can see that the first thing they do is trying with and without initialization from structure from motion. But they show that for the synthetic scenes, such as, for example, the bulldozer scene, or all the blender scenes from Nerve, if you start with randomly initialized Gaussians, it will work, okay? So they start with 100k uniform Gaussians, uniform in terms of position. So they put them in a cubic volume. On initialize they position uniformly. With the adaptive density pruning, those 100k Gaussians will be reduced to 6 to 10k Gaussians, okay? Only 6 to 10k meaningful Gaussians. And then with the densification, after 30k iterations, this will be will increase to 200 to 500k Gaussians, okay? So that here you can really see the impact of the densification on for synthetic scenes. If you start with randomly initialized Gaussians, it's all working fine, okay? Now, if we look at the ablation, so basically that's the first row. No, it's the second row. Let's have a look at the average results, 5k versus 30k. So what's the difference? 5k means 5k iterations of training. 30k means 30k iterations of training. You can see that the difference is huge, right? You have a 20 PSNR when you have a random initialization versus 26. So doing the initialization from a call map or from structure from motion is very important. Okay, so densification, there are two ways to densify. First, there is the cloning. In under-reconstructed area, you clone Gaussians. In over-reconstructed areas, you split the Gaussian and make it smaller. Okay, so here we can see, if we go back to the table, that splitting is the highest impact on PSNR. We drop from 26 to a bit less than 24 when we don't do the splitting. When we don't do the cloning, in terms of PSNR, there is not a big impact, a bit less than 0.15, so it's not huge, but they say that it converges faster when you have the cloning, okay? And even though the PSNR is not huge, they say that it converges to better values or to better solutions with the cloning. For example, thin structure for the wheels of bicycle, for example, that gets better reconstructed with the cloning, okay? So those thin structures do not have a big impact on PSNR, but it's still important. Okay, so next ablation, let's have a look. It's unlimited depth complexity of splats with gradients. So what does that mean? That means that with equation 2, with this sum, right, of n terms, the final color will be dependent on the first terms, right? Because the first terms will have a big contribution to the pixel color, and then later, the points that have a higher depth, there is the transmittance term, Ti, that will attenuate the impact, and at some point there will be the depths that are very far away that are occluded will have no impact. So here the idea, for the gradient computation, we don't want perfect gradient. It's okay if we have either a biased gradient or a gradient with a lot of variance, right? That's the bias variance trade-off. Maybe that's a bit different, but you know, depending, we have some algorithm that have biased gradients or that have variance in the gradients. On it's okay. We can still learn with those kind of gradients. But basically here the issue, what they try is, okay, when I'm computing this gradient, when I go to equation 2, I will only take the Gaussians with the 10 Gaussians that are closest to my pixel. So when I do this, the computation of the gradient, I'm not using all Gaussians, I'm just using the Gaussians that are the closest to the pixel. On this, if that has a big impact or no, but it has a huge impact in terms of PSNR. For example, a drop in quality of 11 decibel on the truck scene. Let's go back to the table, for example. Yeah, you can see on average, you have a very huge drop. You go from 26 to 19. It's even worse than starting with random initialization. So it's very important to have proper gradient or not to do approximation. The gain of doing this approximation, of course, is speed. It would have made the optimization much faster, but it seems that it's not worthwhile. Okay, we've already discussed that, the covariance, the anisotropy of it. Anisotropic again means that the Gaussian can look a bit like ellipsis, right? The extent of each direction can vary. When it's isotropic, which is a very standard way of modeling Gaussians, okay, usually we make them isotropic or even isotropic with a standard with a scale of 1, so with a standard deviation of 1. But anyway, so basically here they say that yeah, the anisotropy improves significantly the results on the ability to align with surfaces. So yeah, that means that if you want to model a wall, for example, the fact that it can, in a way, yeah, you can really like shrink the Gaussian or to modify its shape so that it aligns with the wall. But if it's isotropic, it's just like a kind of ball, right? And therefore it's more, yeah, it's less good in a way. And we can see actually, yeah, in terms of PSNR, that's okay. You go from 26 to 25, well, less than 0.1 decrease, so it's not dramatic. But yeah, it seems that it's better to be anisotropic. As was shown on figure, yeah, on figure 3. when you analyze other Gaussians that have been learned, you can really see that they are anisotropic. Yeah. And I think there is a last ablation to check. Let's have a look at it. Spherical harmonics. So again, spherical harmonics, they allow to model this reflection effect. Okay, if I'm looking at this table, I don't know, let's have a look. I'm not sure if for example, here you can see some reflection. Okay, if I'm looking at the exact same point, but moving around the table, the color of this will change. Okay, if we do not use spherical harmonics or any other way to model that, then that means that every 3D location has a given color. So basically the color, it's not dependent on the viewing direction. Or spherical harmonics will allow to modulate the color as a function of the viewing direction. And if we have a look at in the table, when you don't use spherical harmonics, okay, in purple, okay, the PSNR drop is not so huge, so you go from 26 to 25.35, so a 0.7 drop. But again, you will be limited. You won't be able to model those effects. Usually, you really want those effects. What that means at a given point, from different viewing direction, it has different colors. So basically, that means that if you do not model that, the color will just be a kind of average of all your colors from your images. And also, when you create a video or when you move in your scene, it will look less realistic because you do not model those real light effects. Okay, let's dive into the limitations. Again, they say that they use the same hyperparameters for all scenes, but they say that for very large scenes, they realized experimentally that if you reduce the positional learning rate, I was going to say it gets better results, but it seems that it's even a necessary condition to converge in very large scenes. Of course, since this initial paper, there have been a lot of papers, for example, some that are dedicated to reconstructing very large scenes. Yeah. So that was one of the limitations. On another one, yeah, okay, they mentioned that training can consume a lot of memory, especially in unoptimized prototypes without proper CUDA kernel or without proper optimization of the training script. But yeah, when we compare Gaussian splatting to previous approaches or to NeRF, it's really a huge, it's really day and night. If you want to render those frames with NeRF, at those resolution, I'm not sure about the resolution, but it should be around maybe 720p or higher. With NeRF, it will take minutes to render those kind of images. On here, you can do that at 135 FPS, which is really huge. Yeah, for example, here we have the state-of-the-art results in terms of quality for NeRF. On the FPS is 0.071. So basically, Gaussian splatting is more than 200 times faster than MIB-NeRF. You can also compare training time. So yeah, that was it for this paper. I really hope it was helpful. And now let's dive into the implementation.